We have seen so far cases in which the objective is to maximize the extraction of biomass. It's purely biological, basically. And the question central here is what happened when we account explicitly for the cost and benefits, the monetary cost and benefits of exploiting a renewable resource, fishery. And this led us to basically the Gordon bioeconomic theory of exploitation of renewable resources. So let's assume that P is the unitary price for biomass, so per kilos or pounds, and C is the cost per unit effort. The revenues is computed then as the yield multiplied by the price. And we have seen that the yield can be often described as Q times E times M per unit time. So it's going to be P, Q, E, M. The cost is proportional to the effort E. And so the overall cost of exploitation in any given time or year is going to be equal to C times E. The profit, of course, is the difference between revenues and cost. And we've seen that we can express revenues as PY and cost as overall cost as a small c, the unitary cost times E. And then we can basically write this equation here that allow us to compute the effort as a function of the stock M and the exploitation effort E. Of course, M is not constantly dependent upon the exploitation effort, and that's something that we need to analyze. Now, in essence, the Gordon model can be described in this way. So we have the equation that describes the dynamics of our stock, our population, the stock recruitment function, Fn, minus the harvesting component, minus QEn. And we can assume that effort is not constant, but is proportional to profit, in the sense if profit are positive and are high, there is an incentive to increase the exploitation effort, or it's an attraction for other operators that are outside of this market to enter this market. So it is to increment the effort. And if profit are negative on the other end, there is going to be an incentive for people to leave the market or to reduce the fishing effort. Well, we can use the method of the isocline to show that if we report on this diagram biomass on the horizontal axis and effort on the vertical axis, where effort is not constant but depend upon the exploitation of the resource, well, what we can do is to basically report here the vertical equation is going to be given by dE over dt and provide the values of the biomass, and the straight line represent dN over dt equal to 0, the non-trivial isocline of this system here. And we can show that if we start from an unexploited resource and we start to exploit this resource, the trajectory will go either through a spiral or just directly there, depending upon model parameters, to this point here, which represent the long-term equilibrium in terms of population, biomass, and effort. One interesting and in aspect here, if that equilibrium is characterized by the spiral, we're going to have a period of overcapitalization and strong overexploitation when the effort is really high, and in fact the resource will go well below this whatever level is going to reach the long-term equilibrium. We have seen here basically that if we describe this function here, we represent the revenues in whatever currency, for instance, dollars, that is given by PY and is described by this concave function here. And the exploitation effort CE is represented by this straight line. So basically, the revenues is a unimodal nonlinear function of the effort, and the cost, the overall exploitation cost, is a linear function of the exploitation effort. Now, here where the profits are positive because revenues here are larger than the cost of exploitation, there is an incentive to increase effort. And if we go to the right of EB, the cost of exploitations are larger than the revenues, and so there is an effort to reduce the fishing mortality. So what it turned out is that this point here is a stable attractor, is a stable equilibrium where the system of the stock and effort systems will eventually tend. An open access resource, according to the Gordon theory, will inevitably go to the bioeconomic equilibrium at which P is equal to 0. So the effort is completely vanished in the profit is completely vanished because the effort just tend to go there where the profit are, the overall revenues are equal to the cost. Here, what we can see, there is an interesting property that the effort EB is certainly larger than the effort that maximizes the sustainable yield in this population, which would be roughly at this level here, which is very relevant. So the A resource is over exploited, basically, and the resource biomass is not really the level of the long-term equilibrium of the resource biomass. It's not really related to the biology, but mostly to the unitary price, the unitary cost, and the exploitation efficiency. There are no single biological parameters, as we can see here. We also mentioned here that the total profit P, the net benefit to the community that is exploiting the resource, is completely dissipated. And this actually, you mentioned before, I'm sure that you wonder what does it mean that profit is 0? And the reason is that the cost that we're using here is not just the direct cost only, but it's the opportunity cost of exploitation of this specific stock. Opportunity cost is technically, by definition, the foregone benefits that would have been derived by a more profitable option that has not been chosen here. Somebody decided to go and fish rather than doing something that is more profitable. To properly evaluate cost, the opportunity cost, the cost and benefits of every other option available must be considered and weighted against the others. One way to see it is to assume that unitary cost C, in addition to the direct cost, the cost of gasoline and the cost of equipment, current depreciation, well, these costs include also the labor cost that is equivalent to or larger than, for instance, the unemployment benefits or the minimal federal wage, or the most profitable among the available employment alternatives. Okay, so when I consider that unitary cost, I need to add also what I would get if, as an unemployed person, for instance, I would get this unemployment benefit. And so this is an interesting point. So when the profits are completely dissipated, that's mean I still make the unemployment benefits of the minimum federal wage, but no penny, not even $1 more than that. There are interesting implications here because in a thriving and diversified economy where there are really good opportunities, this opportunity cost might be actually pretty high. And when this happens, it means that the slope of the exploitation, the overall cost function is pretty high. And so there is the possibility that resource is even underexploited with respect to the peak year that correspond to the maximum sustainable yield. On the other hand, in economies where there are very little alternative, which is the typical things that happens in subsistence economies, in rural economies, the opportunity costs are really low because you either get out and fish and sell what you can, or there are not really a lot of other employment alternatives, or if they are, they are not really profitable. In this case, the opportunity cost is actually very low. And when the opportunity cost is really low, inevitably the resource tend to be overexploited because the equilibrium point where revenues are equal the overall cost of exploitation occurs much on the right, so for much bigger effort, the effort that guarantee the maximum sustainable yield. Regulatory methods, therefore, should be introduced to decrease effort, thus generating basically economic benefit to the society and reduce the risk of extinction. So to maximize the net benefit P to the society, what we need to do is to see where, basically we get profit as a function of effort. It's a unimodal function. So in order to get the maximum of the profit with respect to effort, I can compute the first derivative of P with respect to E. And because the profit is equal to revenues minus cost, when I apply this, what I actually get is that the derivative of the revenues with respect to effort needs to be equal to the derivative of the cost with respect to effort. But we have seen that cost is equal to C times E. So this derivative is just equal to C. And so the solution, which is here, so we get a tangent line that is parallel to the line of the overall cost. These correspond to the maximum sustainable profit. And it is obtained for an effort where the so-called marginal revenues, so the rate of change of revenues with respect to effort, are equal to the marginal cost C. That is how the effort, the overall cost change with respect to effort, because it's a straight line. Okay, so there is a way, and there are possibilities of regulating the fishing effort to achieve the maximum economic return in the long run that we have referred to here as E0. This is usually to the left of EMSY, that is for effort that are smaller than effort that maximize the sustainable yield or biomass of extractions. And so when we regulate the fishery according to the maximization of the net benefits, we are often in a good conservative position, if that is possible, of course, to obtain it. Now, let's go forward here and talk about policies for constant fishing effort in discrete time, in this case, with a stock recruitment relationship. These are slightly different the way we describe, but basically is the same concept. We have the generation or time, here the horizontal axis. We have the parental stock at the generation K and the generation K plus 1. We know that we have a stock recruitment relationship, which we'll indicate again with F of PDK. It's in discrete time only at this point. And then, so if this is the recruitment, the population after recruitment, and this is the length of the fishing season, which is delta capital T, and then we start to exploit the resources with the constant fishing mortality, what we get is dN over dt in continuous time, in this case, is equal to minus fishing mortality F times N. And we know that the fishing mortality is described as the product of the catchability coefficient Q and the exploitation effort, okay? And this is what we get. So we can get the population at the end of the generation K plus 1, which is whatever is left. And the difference between recruitment and what is left at the end of the fishing season is, of course, the harvest. Well, if we understand this graphically, let me go down to the formal representation. We say the delta T is the length of the fishing season. QE, which is also referred as fishing mortality, is the instantaneous fishing mortality E. And when we integrate this dN over dt minus Q En, what we got is here the E minus Q E delta T. And this is the fraction of the stock surviving at the end of the fishing season. It's clearly, if E is equal to 0, E to the power of minus Q E delta T will be equal to 1. So all the stock that was recruited here will survive to the end of the fishing season. For increasing E, the fraction of stock that survive at the end of the fishing season will be exponentially decaying, and faster if the fishing season is longer, and faster if the catchability is larger. If this is the fraction of the stock surviving at the end of the fishing season, 1 minus E to the power of minus Q E delta T is the fraction of the stock harvested at the end of the fishing season. Therefore, we can describe the model in this way. The stock at the generation K plus 1 is equal to the recruitment minus the harvest. And the way we have derived, we can write this as F of PDK times E to the power of minus Q E delta T, which is this basically the fraction of the stock surviving at the end of the fishing season. Therefore, the harvest, as we mentioned, is the difference between P K plus 1, which is represented here, and FP, which was the recruitment. And this leads us to write this equation that is FP times 1 minus E to minus Q E delta T, which is the fraction of the recruitment that has been harvested. So let's look now, what are the implications if we are implementing a constant exploitation effort in the case of discrete time stock recruitment relationship. Okay, so we assume that that E, the effort, and delta T are constant in time. And in a lot of cases, we'll see models in which delta T is subsumed into Q. And so we won't see that explicitly because we'll be included there. Okay. We know that at equilibrium point, because it is an equilibrium, P of the generation K plus 1 needs to be equal to P at the generation K. And that's been equal to P. Okay. So, but we also know, and when we, substitute this here, so in place of P, K plus 1, we report P, and so we get P is equal to FP to E to the power minus Q E delta T. And so we can also see that as FP is equal to P times E2 plus the power of Q E delta T, because we basically bring this to the other side of the equation. And basically this means that if FP is the stock recruitment relationship in the PK plus 1 plan, we know that the equilibrium point, this relationship needs to be equal to P, which is the straight line with slope equal to one ingredient of 45 degrees, to E to the power of Q E delta T. This number is actually larger than 1. That means that the slope is larger than 1. So rather than having P, we get P to this slope, E to the power of Q E delta T. So we pivot in that straight line, the 45 degrees upward, to get the new equilibrium point under a exploitation level E that we assume to be constant. Okay, and the difference between the recruitment and what we get here represent, in fact, the harvest. So the sustainable yield is the difference between the red line here and the green line here. So it's F of PEQ, which for here, minus PQ, which is represented by this segment from 0 to the the diagonal 45 degrees, and this difference is going to be equal to the harvest. In order to get the maximum sustainable yield is the maximum with respect to E of the difference between the recruitment function and P. Okay, and so I can derive this, and what I get, that we get maximum sustainable yield when we use an effort that bring basically the population to a level in which the derivative, that is the slope we're going to depict here, with respect to P is actually equal to 1, or this 45 degrees line. So this is the case that the level of population density and the effort at MSY that guarantee the maximum sustainable yield of the population. And therefore, we can derive then e to the MSY is equal to 1 over Q delta T times the logarithm of F to PMSY divided by PMSY. And so we can derive explicitly what is the effort that will lead to maximum sustainable yield. What happens if we have a Lee effect? Well, it's exactly as we see for the continuous time. There might be effort in which, or might be cases, sorry, in which when we try to maximize the sustainable yield and going there to that level of effort, that the basically the stable equilibrium and the unstable equilibrium will get closer and closer. So we converge, potentially even to collapse and to go to the situations where we get a semi-stable equilibrium that will eventually lead the population to collapse once we account for the vagaries of the weather. Okay, so with the policy based on constant effort and a Lee effect, there would be still the risk of instability and resource collapse depending upon the shape of the stock recruitment relationship. Though, how can we address that in a way that we avoid this to happen? Well, we could set up a minimum level of escapement and basically say that if the population drops below that level, we're not going to harvest. We're going to close the fishery. And if it is above that level, the recruitment, well, we're going to remove everything that goes above, the difference between the recruitment and this threshold level. Okay, basically, the harvesting policies can be described this way. Harvest at generation K is equal to 0 if the recruitment is smaller than this constant escapement threshold value, and is equal to the difference between recruitment and the threshold value if the recruitment exceed the threshold value. It can be described this way, so that would be the minimum escapement, basically. So what we would say is no less than that. And if the population, if their recruitment, so if we have a population of this density, we look at the recruitment, and if their recruitment is below P mean, we're not going to remove anything. But if it exceeds P mean, we're going to remove everything between the recruitment R and this minimum level of escapement that we want. So this is a policy that is sort of implemented, sort of an insurance, because it does anything possible to prevent for the population to drop below the unstable equilibrium point. So it's a very conservative, and it's definitely minimize the risk of collapse of the population. There is a drawback, of course. There is always a catch, and the catch that in the bad years, the fishery is closed. And so there's not going to be to generate any profit. And in some cases, this, of course, in a lot of cases, this can be economically and socially unsustainable and not acceptable. And so that's become a problem, because either subsidies are implemented to help the fishermen to go through the season to the next season, or there are going to be problem, of course, to implement this fishery. Now I want to go to the last point and think about two other spatially explicit type of management that are, for instance, considering a network of no-take zones or no-take areas as part of optimal fishery management. And this is a problem. I just want to mention that briefly, and I'll be happy to refer you to papers, of course, that have analyzed this problem from a lot of different perspectives. To show you the results of a research paper is literally one slide for this and another slide for another paper that we published in our group. This was led by Marisa Rossetto, a former graduate student, who developed basically a model of the abalone fishery management in Baja California with specific reference to Isla Natividad to understand whether a network of marine protected areas or no-take zones can be part of optimal management. And there are a lot of figures on this slide. Just to mention that Marisa looked at, for instance, to estimate mortality rate as a function of body size of abalone. We use data that represent somatic growth of abalone, so how much it grows, and account for the plasticity of growth explicitly. And then we get data that allow us to understand what is the settlement given a certain level of productions of eggs, of spawners, and identify a relationship between reproductive output and settlement. We use information to identify what is the fraction of reproductive abalone as a function of body size, and also to look at fecundity as a function of body size, because the investment in gonad is really high in these broadcast spawners, and large abalone produce a disproportionate number of eggs with respect to the same numbers of smaller abalone for the same biomass. And so there is an exponential increase of eggs production with respect to body size. Another element that we consider was that we want to track at this point of body sizes, so we consider stage structured models with finite classes and of abalone of different sizes, and we develop spatially explicit models that are represented by a torus, so a belt that goes around Isla Natividad here in the different fishing zones, and different patches of, say, 100 meters each along the 15 kilometers line, and accounting explicitly for dispersal of the abalone larvae with respect to a distribution kernel. And we analyze these dynamics. The little figure here is not meant to be read in details, but to look at AMPAs or notic zones of different size and different level of protection of the overall population. And the take home here is that there is optimal distributions of notic zones and optimal protection level that allow to maximize the catch in the long run, by using a network of AMPAs. When we compare this to the best maximum sustainable yield in absence of any spatially explicit type of management, what we see is that MSY with no spatial management is actually larger than the MSY with MPA. And so this aspect is not particularly good, right? Because we want to maximize the sustainable yield. But there is also some positive aspect that if for any reason, like we overestimate the abalone density, the stock in a given year, or if there is some level of that is pushing effort above the harvesting rate that maximizes sustainable yield, you can see the catch effort data dramatically drop very fast. And so if we exceed, we're going to catch much less. And here is much flatter, which is good because it's more forgiving with respect to error in the estimation, basically, of the stock size of year-to-year variability. And so this policy increases resilience against stock assessment errors and other type of biases. We look forward to look at if a network of MPAs might also help against extreme events that we are starting to experience more and more because of climate change and the warming of our oceans. And we did this analysis by accounting explicitly for the Allee effect, looking at data by Cinzia Catton and Laura Rogers-Bennett, who have done an awesome job in characterizing abalone demography, stock abundance, and dynamics for many different abalone species along the Pacific coast. And when we account that, we get these results here. It is actually quite complex. Here on the horizontal axis, we reported 20 years catch average, and here the proportion of replicates basically that in which the population has been able to recover. So it's basically the probability of a population to recover given certain level of frequency and intensity of catastrophic events. And what we see here is that for any level of mortality associated with these extreme events, like 90% mortality or 75% mortality for an extreme heat waves that basically wipe out the population, what we see that in the case of no closure, when the mortality caused by this extreme event increases, at some point the catch decreases and the proportion of those that recover basically becomes negligible. So high potential catch, but with really high probability of collapsing. If we implement a network of MPA, what we see that basically the catch is smaller for a given level of mortality than in the case of no closure, okay? But the proportion recovered remains basically nearly to 1 up to 80%, and even for 85% and 90% remain anyway largely superior than in the case of no closure when mortality increases. We also look at the case of dynamic closures when we close the fishery after a catastrophic event. This is probably the best and the safest way to protect the stock. But what actually happens is you see that for the same level of mortality, like you're 85%, of a catastrophic event caused by the catastrophic event, basically the stock becomes zero. And this is because if the catastrophic mortality increases, the length of the closures increases more, even exponentially, more than linearly. That's mean the dynamic closures, it's a possibility, but it's really against any fishery performance and fishery output. And so it can hit really hard the fishing community in the protection. But a natural MPA represents the best trade-off between supporting catches and minimize the risk of extinction. Given that, I just want to finish saying that, of course, it's never black and white. We haven't always considered, except for the last case, the vagaries of the weather and extreme events, as we did in the paper with Emil Alto, a former postdoc at the Hopkins Money Station. The reality is that we need to use a portfolio of strategies, right? And I just want to report here this Rebuilding Global Fishery paper on Science 2009 by Boris Worm and many other distinguished fishery scientists. And the result here that I think is important, that combined fisheries and conservation objectives can be achieved by merging diverse management action, including catch restriction, gear modification, and closed areas, no-take areas, depending on the local context. And so this is certainly a really wise suggestion that we should take account by moving forward. Thank you for your attention.